morning to all of you in the MOOC course on smart materials and intelligent system design. In this series, the first module in which I am talking about the overview of smart materials. On that we have already discussed about the piezoelectric materials. Also I told you about how to prepare piezoceramic actuator. I have discussed about the constitutive relationship of piezoelectric material, which is very much similar, which I will be talking about today also for magnetostrictive materials. And I have also discussed about piezoceramic polymers and composites. Basically, I told you that the necessity for this kind of systems are more from the sensor point of view and also to embed them in structural systems. And also I have touched about the issues of bimorphs and piezo stacks. So, with a broad overview with you on piezoelectric materials, we will now talk about the magnetostrictive materials. In this series, what I will be talking about is that what is magnetostriction first of all, and then I will show you some examples where we can apply these magnetostrictive principles and we can develop transducers based on that. A brief history of magnetostrictive materials, that timeline, how things are evolved and what are the different effects of magnetostriction, along with I will also talk about the constitutive relationships in this case as well of the magnetostrictive material. So, let us first start with our first aim to understand that what is magnetostriction. The magnetism itself is considered to be a magical power for a very long time. It seems that Cleopatra used to take bath on ferromagnetic beads, considering that she will be aging process will not happen to her. So, these are the kind of superstitions or beliefs that were there on magnets in the people. But one interesting thing was only discovered around 1842 by James Prescott Joule, and he noted that a ferromagnetic sample change its length with the application of magnetism. So, that was something new. Earlier people knew that how magnetism is generated in a ferromagnetic material to some extent empirically, but that it also changes its length was not known to people. The ferromagnetic materials can change its length while subjected to the magnetic field. That was a new discovery by James Prescott Joule, and that is the beginning of magnetostriction. Now, what is magnetostriction? Well, if you know about the domain theory that you have studied in your school days about the presence of magnetic domains in a magnetic material, then each one of these beads are actually these magnetic domains, and the direction of the domain magnetism is shown with these arrows, which is very similar to when I have shown you about the dipoles direction of polarization. Now, in general, when h equals to 0, these domains are all placed in a manner that it is a north south combination, but they are not aligned. So, they are very randomly placed. If I apply a magnetic field, what will happen? All these domains will flip and they will align themselves in a particular direction. The moment this will happen, you will see it is like a kind of a twisted chain, and the moment you are actually applying some kind of a force, in this case is the magnetic force, this chain unfolds. So, as a result, this magnetostriction is going to happen. That means, this whole sample is going to change its length. This particular process, we also say that this is due to domain migration and reorientation. That is the way we technically define this term. So, under the effect of magnetic field, when there is a domain migration and reorientation of the magnetic domains, that actually causes the magnetostrictive effect in such a system. If this effect, it is observed that if the ferromagnetic material is initially at a compressed state, then the effect is more pronounced. Well, it is naturally so, because when it is at a compressed stage, then these domains are all much more constricted in a smaller area. Now, the moment you are applying the magnetic field, assuming that you have enough magnetic field available with you, this compressive confinement actually is taken over. So, it comes back to its general normal size, and then as the magnetic field is applied further, it expands until all the domains get nicely oriented in one direction. So, as a result, that effect becomes much more if it is initially compressed. So, that is one technique that people do. The other point is that, is the magnetostriction uniform in all ferromagnetic material? No. Different ferromagnetic materials show different degree of magnetostriction. For example, iron, which was the first one to be noted by Joule, that shows only 14 parts per million strain that you can produce. So, it is an active strain. We will always tell this in terms of free strain. These are the terms that we will continuously deal with, free strain or active strain. So, what it means is that if I do not apply any other external force, then let us say I have a sample of any smart material. In this case, it is a magnetostrictive material, and I am applying a magnetic field, and what is the free expansion that is going to happen to the system. So, that is what is our free strain. We usually denote it by lambda, or epsilon free. So, that is the free strain, that is 14 parts per million in the case of iron, and in the case of other materials, like I will come to nickel later on, cobalt it is 50 parts per million, permalloy 27 parts per million. Towards the end of the last century, or even today, what is happening is that new materials people are actually designing, and in these materials the effect of magnetostriction is actually much higher. Sometimes it is even 100 times more than what we used to see in the age old magnetostrictive materials. So, what is the tricks for that? Well, if you look at it, that in such materials, along with a ferromagnetic material like let us say iron, you are also using another material from the periodic table, which is far away in a periodic table. These are called rare earth materials like dysprosium, like terbium, or a combination of terbium and dysprosium. So, this kind of materials show large what we call giant magnetostriction, and this is the latest development in terms of the material advancement. Now, that is one point. The other point is that in among all these materials, nickel shows negative magnetostriction. So, that means most of these materials, if I apply magnetic field, it will expand, but there is this anomaly there, that is in nickel, that instead of expansion it will compress if I apply the magnetic field, and this has to do with the orientation of the magnetic domains in nickel. So, that is an anomalous behavior. The other interesting point here is the Curie temperature. If you remember, I told you that for piezoelectric materials there was a Curie temperature. Beyond that temperature, if you heat up the material, it will not show the piezoelectric property. Similar to this, for the magnetostrictive material also, if you exceed all these temperatures for various materials, they would not actually show the magnetostrictive effect. That means, even if you apply magnetic field, the domains basically will be so much thermally agitated that they will not be able to align themselves towards the direction of magnetic field, and hence magnetostrictive effect will not come up. So, this is a point we have to keep in our mind. Now, let us just look at a brief timeline how these magnetostrictive materials evolved. As I told you that around 1842, James Prescott Joule first discovered it in nickel and later on in other ferromagnetic materials. Now, 1865, Villari discovered what is known as inverse of Joule effect. So, just like piezoelectric material, where we have seen that if you apply mechanical force, it was generating charge. In this case, first effect was of course the indirect effect, that means if you apply the magnetic field, it was changing its length, but later on it was found that if you change length, it will change its state of magnetization, which is what is the Villari effect. And then people also find that this effect is very important, that this effect is anisotropic. Now, what do we mean by isotropic and anisotropic? It is the same that the way we discuss it in the context of solid mechanics, that this magnetostrictive effect has a directional dependence. So, it is not that in every direction you will see equal amount of expansion. There are certain directions, for example, we call them to be the easy axis. Along the easy axis, you will see that maximum actually deformation takes place, or maximum change of length takes place. So, and in other directions it is less. So, there is an anisotropy. So, that was discovered by people. And then I was telling you that as late as 1965, okay, imagine that 1842 the effect was discovered, but as late as 1965 people first found out that if you use terbium or dysprosium, you will see much larger effect of magnetostriction. This was discovered by Clark at the Naval Ordnance Laboratory of USA. And later on Clark himself have shown that if you make an alloy of terbium iron and dysprosium iron, then you can improve this effect in the sense that terbium or dysprosium on its own shows the magnetostrictive effect at very low temperature, but you can bring it to a considerably high temperature by making an alloy with iron. So, thus actually terbium and iron and dysprosium, these three materials are added finally, and the Naval Ordnance Laboratory name goes inside it, and the material that is used commercially today is called terphenol D, which is a magnetostrictive material. People, just like the ceramic things, started thinking about can we make a polymeric version of it, because that is important for productization. So, 1994 polymer matrix and terphenol D particulate, people have shown like Sandlunds and others that you can make a composite out of it. Also terphenol D, one of the problem with this material is its machinability. So, from that point of view, instead of terbium, it was found out that if you add gallium, then you get a new material called gunphenol, and that is a more rugged magnetostrictive material. And also people have worked on magnetostrictive particles, very fine nanoparticles, and then orient them at the particulate composite phase itself. So, these are various advancements that are happening in the realm of magnetostrictive materials. These materials, in comparison to their the piezoelectric counterparts, they are actually very high energy content they have. In fact, they are like quite explosive. In this particular small video, you see that if I strike a terphenol D material with a hammer, you will see that how explosive this whole system becomes. So, you can see that the energy density is phenomenally high in this particular system. So, that is the terphenol D. Now, let us compare this particular smart material terphenol D with respect to its two other counterparts in the two sides, that is a piezoelectric material and a shape memory material. Now, if you consider in terms of the elongation of the maximum strain that you can get from these materials, you would see that piezoelectric materials give only 0.1% of strain, whereas magnetostrictive material is much better, it gives 0.2%, and shape memory alloys gives much higher 5% of strain. So, that is something which is to be noted, that terphenol D is better in terms of active strain. Energy density wise, you can see that this is 20 kilojoule per meter cube, which is much higher than the piezoelectric material or the shape memory alloy. Bandwidth is not as high as piezoelectric material, it is slightly lower. So, this is 10 kilohertz. Hysteresis is much less, but the cost is much high. So, So, this just gives you a kind of a comparison between the two. Now, I am continuously telling you about parts per million. So, what does that means in terms of giving you some kind of a physical idea about parts per million? So, in x axis I have given you the length here in millimeter. So, this is in millimeter. So, let us say if I choose 100 millimeter of a terphenol D rod and I told you that it shows about 2000 parts per million. If it is not compressed, then that would mean that the change of length will be something like 0.2 millimeter. So, that will give you some kind of an idea about how small is this change of length. In fact, if it is piezoelectric material, it will be how much? Something like 0.09 or so. Okay. So, it is even smaller, and if it is shape memory alloy, it will be something like, right now it is 0.4 is the maximum here, but it may go something like 0.5 millimeter or so. So, that is the highest we are talking about. So, you can get an idea about what is the length change. Can you see it with naked eyes? Well, unless it is a high frequency vibration or situation like that, you cannot see it otherwise, okay? Except for shape memory alloy wares or electroactive polymers, you really cannot see most of the cases that this change is happening, but you can feel the presence if you can develop a dynamic situation like vibrations, etc. Now, if you look at the stress strain relationship in these materials, that is also very interesting. We often call it as a butterfly curve. So, what does this butterfly curve means? If I consider the smaller one where it is not compressed, you look at it that if I apply positive load and stress it, I am going to get positive strain in the system. So, that means if you take a small sample of the terphenol D rod and if you apply tensile force, you are going to get tensile strain, which is fine, it happens. But interesting thing is that in this case this load is not coming, first of all, not by a physical load, but by a magnetic field. So, this is an OR state as you have seen. So, if I apply a magnetic field and that magnetic field matches with the direction of orientation in a manner that it actually gives you the tensile stress, then it is going to expand, fine. Now, what if I change the direction of this magnetic field to the reverse direction? Okay. In the case of piezoelectric material, if I change the direction of voltage, it immediately starts to compress. But in this case, if I go to a minus 1000, okay, if I look at it, well, it is exactly the same as it was at plus 1000. So, that means it is still giving you positive strain. So, that is important, that magnetostrictive materials, they always expand no matter whatever is your direction of the magnetic field. The other thing that you can see here is that if I increase the pre-stress level from 0 MPa to 6.9 MPa, I am increasing, look at the maximum strain value something like say 600 here, and it will be going something like say 1800 here. So, it increases this much if I actually, I was telling that if I apply a pre-stress on the system. So, that is something that we also try to take advantage of. And one last point here is that if I increase the magnetic field, am I going to get continuously magnetic active strain or free strain out of it? No. Beyond a certain level, you see this saturation is occurring. So, that is technical saturation of the system. That means, beyond that strain, you are not going to get any more strain out of the system. Why? Because all the domains are aligned by then. That picture I will show you soon, that how these domains change. Now, where can we apply such a system? Well, one of the most important application of such a system is in terms of tactical acoustic littoral ocean networks, TALON. So, these are sonar systems. Sonar systems are used for defense purposes. Say for example, if there is a underwater attack of any submarine or any such thing, then this kind of systems, these sonar systems, what it does is that it actually converts the the mechanical field of wave in terms of change of magnetization, and that change of magnetization actually generates a pickup voltage in the system. So, thus you can actually develop a magnetostrictive transducer by using the magnetostrictive material in it. So, if you remember earlier we have used piezoelectric composites. Okay. In this case we are using a magnetostrictive material. Let us say this is a block of magnetostrictive material in which an wave is hitting. We expect this material to actually vibrate in this manner. Okay. Now, let us say as it is vibrating, mechanically deforming, so its state of magnetization is changing. If we have a coil here, a coil like this, which we call a pickup coil. Okay. So, in this pickup coil, the state of magnetization will be changing in this material because of its change of length. So, this pickup coil, if it is attached to signal analyzer, what you are going to see is that the signal is going to get changed. So, you are going to essentially see in the time domain in terms of the current change, or you can convert it to voltage change equivalently, and you can see that there is a wave or a vibration coming up in the system. So, thus you can actually develop a transducer using the magnetostrictive materials. What are the major applications of this system? One of the major application today is not just for transducers, but for active vibration and noise control. So, in this case what we do is that we if suppose there is a vibration or a noise happening. Okay. So, noise is nothing but a high frequency vibration. So, let us consider that a system which is vibrating at a very high frequency and it is creating noise etc. I want to control this for various reasons like structural purposes, comfortable situations etc. Now, if I use a magnetostrictive material in it, so suppose I am using a magnetostrictive material, then and if I actually have a coil around, what will happen is that I can give whenever it is expanding, I can give a compressive stress. So, that it is forced to go back to its neutral situation. So, like that in the other direction also I can do the same thing. So, that is how the active vibration control happens. So, this essentially forces this situation back to the neutral location. Machine tool chatter in a very similar manner you can control. Servo valves, it is also used for on off type of valves, hybrid motors, sonar devices I have already told you, automotive brake systems and micro positioner very similar to the servo valves, and also for ultrasonic cleaning of machining where you need to generate high frequencies. Okay, and also for ultrasonic welding purposes you can use a similar magnetostrictive material. What is the one of the advantage of this material over piezoelectric material is that piezoelectric material, because it is basically capacitor in nature, it may actually get discharged with respect to time, but magnetostrictive material would not do so. So, it is actually more rugged. Now, this is what is like what happens if I apply a magnetic field of intensity H, and I told you that it will change its length no matter whatever is the direction, it will change its length to L plus delta L, and you can see that this is how this change of length is happening to this system. Now, the reason why I am showing it is that can we develop alternating modes in this system. That means, if something only expands, you cannot actually get a, like if you consider that earlier example that both positive and negative displacement, okay, that means tension and compression from a system, how can you get if it only expands? You cannot get it, right. So, in order to get that, what we do is that we pick up somewhere we apply a bias magnetic field. So, if I apply that, then the system is already it is going to expand to this particular value. And then with respect to this, if I reverse the magnetic field, what is going to happen is that it is going to show the both sides expansions, and as a result you can generate vibrations in the system. So, this is actually something like it operates against a bias magnetic field, and only then the magnetic field value increasing or decreasing, you are either expanding or you are contracting in a relative sense. So, that is what is the trick that we use. Now, if you look at it, that what is happening microscopically is that when there is no magnetic field, the domains are randomly aligned. As I am increasing, the favorable domains are increasing in size. Okay. So, that you can see that there is a partial magnetization state, favorable domains are increasing. Beyond a certain magnetic field, all these domains are aligned. They need not align directly with this, but they will be aligned towards this magnetic field, and that is what is irreversible domain magnetization. If I increase further, then all of them will actually go and perfectly align with H, and that is the technical saturation. From this direction to this, there is not much of a change, but from here to here, from state A to C, you get maximum part of the magnetostriction. So, this magnetostrictive effect, then we can actually distribute it into several effects. Okay. The first effect that I told you is a reverse effect, the change in length, that is Joule effect. What if instead of change in length the volume changes, then it is called magneto-volume effect. Okay. And what if I do not want to change the length, but I want to twist it. So, application of helical magnetic field can do that. Okay. That is also known as Weidmann effect. And from the direct effect point of view now, if I stress it, the change in magnetization will take place, that is Villari effect. If I actually apply a volumetric stress, then there will be, it is called Nagoka-Honda effect, where there is a change in magnetic state also. And finally, just like the Weidmann effect's counterpart is called Mathieusi effect, where if I apply a torque, I am going to see helical anisotropy and EMF will be induced in the system. So, there are so many variations, at least 6 variations, which are very common in the magnetostrictive material. If I now come to the constitutive equation of magnetostrictive material, then 2 of them that I have chosen, one is the Joule effect and another is the Villari effect. In the Joule effect, what is happening is that, and we call it as the actuator equation, that if I apply the magnetic field, I am going to get the strain. Remember, as usual, if I apply stress, I am going to see the strain, and that is not a smart behavior, that is just that any material would behave. But if I apply a magnetic field and if I get an actuation strain, that is what is important, and that is used in actuators. Similarly, in terms of if I apply a stress and if I see that there is a change in magnetization, not through the application of magnetic field, but through the application of stress, then that is known as the Villari effect. And these 2 equations look very similar to their counterparts of piezoelectric materials. So, if you look at them, that B here is the magnetic flux density. So, that is a new thing to us, which is generally measured as Newton per ampere meter, and instead of permittivity, we have a permeability here, okay, which is measured at a constant stress, and then H is the magnetic field intensity as ampere per meter or Orsted's, we use such units for measuring the H. So, that is for the magnetic field intensity. SH is the compliance, it is a reverse or inverse of the modulus of elasticity, and D is the magnetostrictive constant. Just like piezoelectric constant, we have a magnetostrictive constant here, whose unit is meter per ampere. Now, you see, instead of voltage we are giving here ampere, because you need to give current in the coil, right. So, it is most favorable if I actually give if I use current as the input and expansion of the system that in terms of meter. So, that is why meter per ampere is used in this situation. Now, There are two ways I will show you. So, one I told you for the actuator for sensing applications, either you can develop particulate composites. So, terphenol D particles are mixed in a suitable resin system and cure to develop a sensor, or you can develop actually thin films like metallic glasses as magnetostrictive sensors. So, these are two ways. And in terms of actuators, there is one actuator which is very common, it is known as magnetostrictive mini actuator. So, what you do here is that you have a terphenol D rod here, and then you actually have the energizing coils here. So, the coils basically give the magnetic field. Also you give a bias magnetic field, as I told you that this bias magnetic field allows it. So, if you still remember the H versus the magnetostriction plot, let us say you remember that butterfly curve. So, in order to give this bias magnetic field H B, that is why we are using this thing, and then across this bias magnetic field we actually oscillate the current. So, that I get this variation of strain in it. So, that is what is used in this magnetostrictive mini actuator. There is another very interesting application that you can do using it. You look at this, that you can develop an inchworm which is very similar to some of the earthworm motions by using magnetostrictive material. Look at it, that how people have developed this product, where you are applying the magnetic field, and essentially these expansions are happening in each one of these elements, and they are sequentially in touch with the wall, and and that is happening in a sequential phase. One is touching, one is opening up. So, clamping, declamping, and the whole system is having a forward motion. So, that is something that you will find in this type of a system. So, these are some of the interesting applications of the magnetostrictive material. One interesting application is in terms of pipeline sensing. It is also known as magnetostrictive delay line sensor. So, what you have here is that once again you have these coils here, and this is a transmission coil, and you have a receiving coil at the other point. So, as you are applying an electromagnetic field, what is going to happen is that a vibration is happening, and that vibration, mechanical vibration, is traveling along the pipe. Now, the same signal that you are giving here, you can in no time you can get the same signal back here. So, the electromagnetic wave you can transport in no time, but the actual mechanical vibration signal will get a delay, and these two, if you actually plot one with respect to the other, let us say one signal which is coming. So, it is a time versus I. So, let us say one signal is the electromagnetic excitation that you are happening, that is happening here, and another, if you try to get the pickup coil current, you will see that there is a delay in the whole system. So, that delay is because the mechanical signal takes some amount of time to travel and generate this. Now, this delay can actually be a parameter. If there is a crack, then this delay will be more. So, that way you can actually detect cracks in the pipeline. Now, you can also develop another intelligent applications of the system, which is known as hybrid transducers. For hybrid transducers, what we have is we have a magnetostrictive rods, that is the horizontal part, and we have piezoelectric stack which is vertical. So, what is happening is that by controlling these piezoelectric stacks motion, and in combination with the magnetostrictive rod, you can actually first of all, this will make sure that if it expands, it is going to touch the system. At that time, you with the help of magnetostrictive rod, you get a pushing force. So, it starts to rotate, but if it is in touch with, it cannot rotate. So, you immediately switch it off, so that it goes back. Okay. So, the system goes back, and this whole thing starts to rotate. So, that is one of the use of a hybrid transducer of piezoelectric and magnetostrictive system. There are many other uses, like material which is partly piezoelectric, partly magnetostrictive, or amorphous ribbons with viscous fluid in it on a piezoelectric beam. So, you can produce many such hybrid effects by using both of them. So, this is where we would like to put an end. In the next lecture, we will talk about active smart polymers, classifications of electroactive polymers and their applications. Thank you.